And welcome to the third part. Yeah, no, not quite. This should be body.push param, I think. Or not? No, this should be captured, I think. How does that work down here? Yeah, captures the original lambda. Then we build the explicit parameters, which are the arguments of the two lambda type. And here we say lambda body push param of that type. Here we don't need expressions because we have the builder, and then we just say lambda from return, maybe. There's from lambda type dot return type. And then we have a lambda body. Here we push a call, which is a yogurt call of the capture the from, basically. Okay, so we call that original lambda, that will be the callee. With these arguments. And then we cast that. From lambda dot return type. compile expressions apparently, and then we have this body inside that we can compile. Do that. I think just that. Let's copy that from here. Oh yeah, yogurt built in. Yeah, let's print the debug version, I guess. Oh, it worked. Well, it doesn't work, you know, but wow. One step closer to working, I guess. In the egg we have a lot of functions. A lot of functions. Okay, I'm compiling. I think this is the... haven't yet tried to compile the yogurt. Right. Let me scan for some yogurt thingy. No, it says egg, and then boom. Oh no, something went wrong. So even in the egg, things apparently don't quite work yet. Is big enough. So we call compare on a power and a number. Compare being probably defined in core compare or something, and that should then kind of delegate to core compare delegates to core int compare, and core int compare and here is a local function that probably uses this one, built-ins compare ints. Switched on non-enum. That is unfortunate though. So when converting stuff to egg, things don't quite work yet. Compile fun. We have, let's just see how we do that. We say we have this condition that we switch on. Then we get the type of that condition. And that should be this. Should be an enum. That is true. Let's maybe print the condition. I think it should be self-contained, not containing IDs or something, because that's still toast. Yeah, so the condition is this. A call to compare with two arguments, power and number. Amazing. So why is that call? In case call, maybe these calls, they don't have the correct type. We have the arguments, we have argument types, seems fair enough. We check if that's actually a struct access, okay. If it's a visible variable, then it's a lambda, you know. Otherwise, it's a top level function. And what we do is we find a matching function, which apparently works. We check if it's a built-in function, which it, maybe the built-in function returns the wrong thing, I don't know. But know that we should have some sort of function that we call that is a local function, and we take that function's claimed return type and we compile that and specialize that. Seems fair enough. Signature and substitutions. This one right here is a bit random, I think. Hang on. Okay. Yeah, I think this needs to go somewhere else. Maybe after we have the, yeah, probably in here, right? After we have the signature that we want to use, get the built-in signature. Oh no. Built-in types. This right here is the built-in signature. And oh wait. Before, this doesn't even have condition in there. We see some sort of call, we try to find that call, and then we go over all built-ins, and for the first built-in we'll just do, you know what we're actually going to call that. So it makes sense that that function returns int, because every function call would just call the built-in add function. Yeah, of course we also, like, we need to check whether the signature matches. So if built-in signature equals our signature, only then do we return that built-in call instead of actually calling a function. And if that's not the case, then there must exist a function, and we lower that and compile that and whatever. Yeah, okay. This is weird, however. So function built-ins.mul-ins. Hang on. What do we do? This is still the printing, and then here we do compiling round up to power of rec. Then we compile some OR function, we compile a format function, we compile, oh that works, that is nice. Here we compile the star function, and here things don't work because, oh, apparently this check up here doesn't work. The signature we want to find is this one right here, built-ins.mul-ins int. But apparently this signature is something else. But it should be built-ins.mul-ins of the parameter types, so of int and int. So maybe print else no match. Okay, these don't match because, hang on, why doesn't this match? Built-in signature. Function built-ins.mul-ins and int doesn't exist. Why? Oh. These are all the local functions that are in scope. And those are still like local or imported or built in. So this action needs to happen down here. Oh, okay. We have an egg. That is pretty cool. Yeah, look at that. Okay, so here's the main function. Calls make list, calls sum of that. Amazing. So here we have the yogurt. The yogurt does something called none.unwrap. Compile cast fun body. Let's just see that this yeah, I can check that this is sensible. Well, yeah, that is That is what I wrote here. Indeed. Indeed. Okay, end to end makes sense, makes sense, makes sense, makes sense. That does not make sense. This does not make sense. Yeah. Why is that called? Where is that called? I should maybe also print like yogurt mod. Basically, when compiling a function, this one, egg fun. Yeah, we have the signature. I'm also going to print compiling that signature. Yeah, so the equals function. The equals function does something stupid apparently. Let's look at the equals function. Equals of int and int. Here. We call compare ints. That gives us that. Okay, that is fair. Then we switch on that result. It makes sense. If it's less, then we create this enum false. Here we create that enum true, here we create that enum false, and those get cast to the same type. Yeah, and that gets returned here, that's the type. That does seem sensible. First thing I noticed is that they don't seem, like the functions don't seem to have any sort of prefix for the module. That seems dangerous. Like the signature should contain the module. Crazy. I mean, they do the same thing, so wait, what? I don't get that. Oh yeah, for lambdas. In egg to yogurt mod. At some point we say, please do this lambda thing. I think we'll need, does the context have a module? Do we have a module right here? I don't know, somewhere there should be a module. Module is not in scope, that is sad. And what do we have in scope here? We have all of this. The context doesn't have a module, no. I think we also need a module here that is kind of ugly, maybe. I mean, I can just do that, right? Boom. Simple. Same for casts, actually. This shouldn't have to rely on like types and stuff. No, no, the name is unique. That's the point. Okay. Yeah, that looks better with the module prefix. So we're compiling core int equals. Okay. That has several casts in there. That is true. For example, this one, which casts something from the type false to the type true or false. Yeah, false to true or false. We have another one, but that should cast this one. Five. And I'll cast this one from true to true or false. What is going on there? Oh, I see. These are like internal casts. We're casting this enum here, and this is what a variant that has a value. This is the type of that value. So this is casting the enum, the false variance value. And this one probably doesn't work, and there's somewhere in that cast function that like something goes wrong here. We're casting an enum. Okay. So what do? We have the from type and the to type. Yeah, we know that the to type is an enum, so we want to cast something to an enum. That means we want to build some sort of switch of that to type. Yeah, so we switch on the from value and put in these cases. And for every entry in the from type, so every case that this can possibly be, aka only one case in the case of this one, we get the name, which is false. We get the from value type, that is an empty struct. We get the to value type, that is also an empty struct. This false here stores an empty struct. Yeah, so we say case body is a body builder on that body tag. Yeah, and the from value is going to be a parameter to that of the from value type. The to value is going to be the result of casting that from value type to the to value type. And we'll pass, oh, not the from, but the from value. And here we have the to. Then we just wrap the to value in an enum. Does this work? No, it does not. Let's also say print that here, and down here say done compiling cast. Then we can kind of see which are nested in which way. Okay, so we're compiling the equals function, makes sense. So we're compiling a cast from this to that. So we're first compiling a cast from the empty struct to empty struct, done. And then we're also done with that. Okay. And then we're doing this. In the actor yogurt, do we compile casts anywhere else except here? We shouldn't have to. I think. Hang on, cast dot no. Body with cast. Oh yeah, the entire body already casts the value. So we don't need that. And also this, like, we've checked that. The code is like type checked, you know. And the claimed return type is always the actual return type. So we can just do that. Remove that, boom. Okay, now import cast, fair, and here we have several casts. Yeah. But still happens. Where is that coming from? I don't get it. Really don't get it. And think that there's a lot of expressions here. Oh, well, that makes sense, yeah. We're compiling the main function, and in order to compile that, we are compiling the make list function. So in order to compile that, we compile the equals function. can do like expression with source to kind of get information where that's coming from. That is pretty cool. Well, that doesn't tell us anything, but maybe. Hang on, I think the source, shouldn't that have like, yeah, that should contain a module and stuff like that. I'm also going to write the module down and stringifying them. Yeah, that is true. So here we go. Yeah. Alright, we have compiling workspace core int. One, 2, 0, 8. Yeah, the not full screen version. So here we can say 1, 2, 0, 8 to 9, right here. Okay, this here is our cast. So in that equals function, interesting. But it does look correct here. Let's look at the IDs. We put that empty struct in there, and then we cast this right here, this false, and we return that. We put that empty struct in here, we cast that, and we return that. We put that empty thing in here, we cast that, and we return that. Then we return that overall thing. That does seem correct though. Let's print the this one maybe, or the original ID is ID. Original ID is 6. So this one right here. But the type of that is that. Oh no. Well, I guess this is what I get for having untyped IDs, you know? This right here used an egg ID to get stuff from the yogurt thing. Okay, yeah, so now we have a yogurt. That is pretty cool. And for example, the int equals function, the casts have now been converted into this. Call this cast function, and that is defined here. Yeah, that's cool. Okay, and from there on we can continue to the next compiler stages, to the pudding. There will be some errors, but the cool thing is the pudding shouldn't need to change. The conversion to pudding, yeah, there's some stuff to fix there, but the pudding itself doesn't need to change. I'm just going to very naively translate that into just update that so that it works at all, and then I can make that beautiful afterwards. Okay, I see some tiny bit of commonality in this one. Let's maybe pull that out. Now that is simple. Three. Not sure about that. 93, it only contains these fields. Ah, I see. Because these are children. No? I mean, currently I have these instructions. I want to remove them in the long term, but for now I think I'm just gonna have to put them in here and kind of map them like one to one. So now we have some sort of pudding. What stuff doesn't work? Let's print the signature. Does it have a signature or name or something? Maybe not. Nope. Damn. But we can do that in here. Oh no, that's single expression in here. Yeah. Compiling main, compiling cast. Okay, cast. Cast is apparently weird. Why though? Let's look at the cast from empty struct to empty struct. Here. It returns 0 and that doesn't exist. When we print the body, do we also print the parameters? Yeah, we do. So apparently the ampersand function doesn't even take a parameter. That is not good. So let's fix that. Here we compile some sort of cast function. So what we do is we push. Oh, we do push a parameter though to the from function. The from with the from type, yeah. Then we compile the cast function. Using that bodybuilder. And that from thing is already mapped. Oh yeah, we don't even have mappings here, so of course it is. What does that do though? So yogurt dot I'll compile from. Where's the yogurt bodybuilder defined? In here. Okay. When we push a parameter of some type, we put that into the DAG and we push that to the yogurt parameters. So far so good. Oh no. Yeah, then in the end they get put in there. Okay, same error. But different function, I think. Yeah, different error. So these functions now compile. That is already pretty cool. Where's the struct? Let's look at that. Yeah, now it takes a parameter. Very nice. And returns that. Amazing. So compiling make list of int. make list of int. That doesn't accept anything. That is weird. That's really weird. Why not? From the main function, let's go into compile fun, and if we have some sort of call, what we do is we find the corresponding function. Oh, I'm in the egg. Oh yeah, it's here. I see. Case call. Yeah, so we have some sort of function. What we do is we compile that function. Makes sense. So we are calling this right here, compile this function, which means we have these parameter types, we build a signature from them, we build up these parameters, and then we say, hang on, we have this DAG, and we compile the function body. Using this. Yeah, here we don't care about parameters. Where's the other place where we call compile bodies and switches? Here we also put the say compile the body. Yeah, I think let's change that. Let's say when we compile a body, first of all, for all the parameters, we push, we get the type of that, and we push that to the body. Then we put a mapping in there. Yeah. Then we don't need to do that up here. That's already pretty cool. Is params ever used? No, not really. Oh man. Yeah, this becomes really simple, and that is nice. And down, not here, but in the switch. We also don't need this anymore, because we know the switch body knows what kind of things it expects, and it can just push them. Oh, that worked. And does that look sane? I think it does. Let's see, we have a call int dot minus that has a 0 and a 1 in here. Calls dupe on both integers. And calls sub, the sub instruction. which is like built in, because it imported built-in .subints. Now that is here. Yeah, we dupe the result. Yeah, makes sense. We drop all 0, 1, and 4. Amazing, and we return that. Amazing. That is amazing. Damn. So here we have tube 6. Sure, put that in there. That is nice. Okay. Let's try to enable the rest of the compiler, because the yogurt didn't change. The pudding didn't change. So this part here should just work. Well, yeah, some of that was outdated anyways, like this one. To do rest. Compile module. Wait, what? Oh, here. Yeah, main int is not in the map because main is in the playground module. Hang on. Let's compile to byte code. Oh, here. Yeah, because that's like workspace, something, something, workspace, playground, dot main. Okay, so something doesn't work. Well. Why though? Maybe things get a bit more obvious. So I have a few ideas for simplifying stuff. First of all, when converting egg to yogurt. Yeah, when casting, I think I'll just, I can just check if the types are the same, you know. Hang on, body is, oh yeah, this one. In that case, I'll just return the original ID. Otherwise, I'll compile a cast function. So basically, we won't have cast functions if we try to cast int to int, for example, or empty struct to empty struct. Let's look at that, whether that works. Okay, yeah, so here we still have cast expressions, but when we expand those to the yogurt in here, they kind of disappear. Well, they don't disappear. Interesting. Why not? Oh, that in itself is also in a cast function. I see. So I think we, like, what we really want is to just yeah. Like, here's a cast that makes sense. Let me find something obvious. Yeah, here. Yeah, we call sub-ins without casting int to int before. That's pretty cool. And I think these kind of things, they greatly simplify the code. Like a lot. So yeah, let's also do that in, like, within the cast function. Basically doing where's that? What we do is we call cast. Yeah. And body is a yogurt body builder. By the way, that means that we don't need ampersands here. And I think I'll add something like body.pushCast or something like that, which I'll then use here and up there and so on. Like yeah, something like this. Yeah, push cast, yogurt body builder. Let's just have the from and the to type, because we know we can get the from type from there. Basically, this can then check this sort of thing. So it says we have a from type, we have the to type. If they are equal, then we just return from. That makes sense. Otherwise, we're compiling them. Compile cast from type to type on this context, and we call that function with the from value. So push cast, and then in here we can just do, you know, body dot push cast ID type context. Clean. And we can do something very similar down here, where every time we want to call this cast function, we'll actually just do push cast of that from to the to type with the context, and that only does that on demand, like compiling new functions. That's pretty cool. Yeah, push cast of the from value to the to value type using that context. Same here. Yeah. Damn. That got a lot simpler. Nice. So now there should no longer be any cast, like that the cast functions themselves should be much simpler now. Let's see. We have like a very few cast functions now. That in itself is pretty cool. So casting an empty, casting false to true or false. Yeah, we get the argument. We dupe that. Sure. Hang on, let's do that in the yogurt before we have dupe and drops. Oh, we do have dupe and drops here. Oh, it's the pesto, I think. Yeah. So let's go even further up. Still dupes and drops. Pudding, yeah, this is the yogurt. Okay, so here, for example, casting true to true or false. Okay, that's always true, and it just returns true or false. Okay, that's not yeah, super interesting. Oh, but yes, but it is. Because this right here is an empty struct, and that empty struct is not casted, is not cast to an empty struct, but it's just used directly. That is pretty cool. Yeah. Okay. Yeah. I'm pretty happy. I'm not entirely sure why this like fails, you know, why. Oops. In the VM we have the call function. And at some point we say get ref of the size of addresses. That should be the call stack, I think. Here we say get on that call stack apparently. I don't see that. Oh, I see, we also do this. What's going on here? Okay. Push 1 from stack. Data stack is bytes. That's it. Yeah. That's it. Okay, so this doesn't work for some reason. Index out of bounds. Let's maybe print a nice error message. Use a jump table len. And that makes sense with this 0 to 2, you know, some jump table that has only length of 2, yeah. 170 is quite a big index. I don't know what that's happening. Not quite sure how to debug stuff like that, you know, because it's so I mean, okay, I could maybe do something very simple that still uses a jump table. Such as always returning 0, but before that we call foo of a, and that claims it returns a bool, but actually it just always returns true. True. I need to import that. And already, you know, this is a pretty small example, but the waffle is still pretty big for that. I mean, the pudding is quite small, so that's good. Let's see if this makes sense. We have foo of some integer. So we dupe something, there's empty struct, we create a true variant, that is this. Oh wait, why is there no cast in here? I was expecting a cast. Something like cast true to true or false. Because the foo function should return a bool, but it doesn't. The yogurt is even smaller. Which makes sense, you know. What is this? Oh yeah, here we still have casts from one type to the same type. Yeah. Can we maybe remove that from the egg as well? Like, you know, when converting something to egg. I'm wondering, like, we do. Oh, there's a switch. Yeah. For a switch, we cast the return value. For a function call, we cast the argument values, but we should also cast the return value of functions. So when compiling a function, which is hopefully somewhere here, toast fun, we have this body builder, we push the parameters, sure, we define them, boom, we've returned something. Oh, look at that, we need to cast that. That's true. Basically, we need to check what the function claims it returns. Yeah, this is the returned thing. Expected return type, maybe. And that would be fun.return type. I think that's the thing. Fun.params. Yeah. Return type dot compile module types. No, that's not specialized. Actual return type is, well, this one. So we'll need to add some sort of cast expression here. The body, turn that, yeah. So then we push that returned thing to the return type. That's like the function. The function is responsible for casting that. there's the actual thing that's returned, and we cast that. Let's have a look at the yogurt, first of all. Yeah, we cast that true to true or false. That's what I expected. So here we have that main, and then that cast. Pretty cool. So here we have the pudding. Okay, does this compiles? Okay. Here's the pudding. Damn. Like, I think the next. Actually, I think I don't like. Well, it is difficult to work with optimizations. Because the compiler becomes a lot more unpredictable. Yeah, you change something slightly about the input, and boom. It's quite difficult sometimes to test some pieces of the compiler, because the compiler will optimize too little or too much, you know. But in this case, like, I don't know how to. I mean, I can. Yeah, sure. Let me try to do the original thing, where things didn't get cast between different types, and try to have that same code, make list of length 2 dot sum. Not quite. I think I'm actually not sure. Make list of 2. What does that do? Yeah, list with 42 inside, so the sum should be 48. Anyways, I'm not a guru. A super, like, optimizations make debugging more difficult in compilers. But certain kinds of simplifications I think you can always do. And like removing casts between the same type, for example. Or having a better strategy for dupe and drop things. Or omitting dupe and drop operations that on values that have nothing heap allocated. Like stuff like these, they just remove clutter without touching the actually interesting parts. Advanced optimizations like inlining and constant forwarding and stuff like that, that may get us into like tricky territory. But I think I can maybe make some very obvious optimizations, and that simplifies debugging. That's the idea, at least. So I think that would mean that. So first of all, these casts here. I'm thinking about, can I already remove casts in the, what is it, in the egg that would kind of simplify things. And also, like, that would relieve the pressure on later optimizations. It's really easy to say, I'm going to put casts in here and dupe and drop operations and stuff like that. And then in the end, in the pesto or something, we'll try to optimize that. And like all of that falls away. But it means that these earlier compiler stages, they are really difficult to debug because they are so loaded. So I tend towards not trying to emit too much, but being somewhat minimalistic and doing some of these kind of obvious optimizations earlier. Alright, so yeah, 2 egg on some toast. I think the cast expressions that I have here, genau. We have egg op.cast 3 times for the return value, and we know the return type that we expect here for the enum switch thingies, but we also know the expected type. And for the arguments, I think I'll add something similar to what I did in the next compiler stage, which is have some sort of cast method. I'm going to push cast on, what is it, like egg body compiler or something, egg body builder, yeah. We have this from ID, and we have the to type and the source, and that just results in an ID. And what it does is actually pretty similar to what we did in the cast up here. We get the type, the from type, which is the body dag get from.type, amazing. And then if the from type equals the to type, then we'll just return the from ID, which is totally fine. Otherwise, and this is a lot simpler at this compiler stage, we'll just do egg op.cast. Well, cast from to the to type with the source. This doesn't work because it actually returns nothing. Oh no. But it doesn't though. So let's fix these and instead say, hey body, is that mutable? Yeah, that is mutable already. Push a cast please of that returned value to that type. And here, compiler, yeah, fair enough. And please push a cast of that return thing to the common type. And here we say please push a cast from that argument to the expected type. Okay. But now the oh man, that's a lot of output. Yeah, now the egg is a lot simpler because we have way less casts in here. So true to true or false, that makes sense. But not nothing to nothing or int to int or something. You know? Like these, this is certainly a lot cleaner than before. Yeah. Oh. Oh, and also all these int functions, they are a lot shorter, which also makes the compiler faster because now it uses less memory, you know, to represent all that. These graphs, basically. Okay, then we compute the yogurt. And the yogurt looks reasonably simple, I would say. Yeah. I may want to do some like obvious optimizations. For example, it may make sense to do constant folding. If a function is called with only compile time known arguments, then that function can just be executed directly. But maybe I won't do that right now, because that is a bit more involved. Yeah. Yeah, but I think on the yogurt there are like lots of optimizations possible that we can still do. Maybe I'll look into that next, but not today. Yeah. On the pudding as well, like here, these dupe and drop things, we can be way smart about when to remove them, when to add them. And then at the next compiler stage we can, here in the pesto we can simplify that even further by saying, hey, duping some some enum with no pointer inside. You don't need to do that. You know, duping in general, like duping and dropping types that don't contain pointers is useless. Let's not do that. And you can really see how that tiny bit of code, you know, that kind of explodes throughout these compiler stages. Because these approaches of adding dupe and drop things for everything, of adding casts everywhere, these are somewhat naive. Yeah. Okay, so before going into the yogurt and doing crazy constant folding stuff, I think it's worth thinking about dupes and drops. And basically, values. Maybe I should stop for today. Probably should. But basically, values should be dropped as soon as possible, not just at the end of the scope. Meaning, if you have some value and you use that value, then sure, it has to be duped. Oops. But if you use the value for the last time, then you don't need to dupe that before, for example, passing it to another function. So I think the way to do that would be to kind of figure out when is the value used the last time, basically. I think there are multiple ways to do that. The simplest, perhaps, to just count the amount of usages of each value. Oh, but it is kind of difficult to do globally, I think, because let's say you have some sort of switch and you dupe some value in order to be able to switch on that. I think here we'll basically need to check, is that 0 used somewhere else? If it is, then we should just... not sure about that. Let's write some simple function. That is way more simpler than this. A function that adds 2 and 3. Maybe clear the console so I can more easily get to the top. So this will result in in something that feels quite bloaty, I think. You know, the main function, what it does is it creates a 2, it creates a 3, so far so good. It calls a dupe function on int, which just does nothing. It calls the dupe function for the other int. It puts them in a struct. It calls the plus function. It dupes the result of that. It drops all other functions. And I think these dupes and drops, we want to simplify them. So basically, we insert them when we see that we want to use them, like here, for example. Or like here, yeah. Well, here. Yeah, we see that we want to call something with 1 and 2, so we need to dupe 1 and 2. And then at the end of the scope, we'll drop all of the functions, or all of the values that are still in scope. Let's maybe do a naive approach of being like, we see some call, so then we'll just check for the rest of the function if the 1 is still used. If not, then we don't dupe that. That would be pretty naive, I think, but I think it should work. The question is what happens if the control flow splits. If one part of that uses the value and the other doesn't, for example, then I think I'm not sure what happens then, or what should happen then. I think in the branch where the value isn't used, it then gets immediately dropped at the beginning of the branch, at the beginning of the body. Yeah, something like that. Maybe that is a bit difficult to do. Maybe it is. Okay, but I know for certain one thing that I can definitely do, and that is not duping and dropping values if they contain no pointers. That is something really obvious, and I think that actually that's the case for many values. So that would be in the pesto, put into pesto. So we have some sort of dupe and drop here. And we can basically check if function get value dot type compile dupe from. I think we'll just check if the value on this also does dupe. Oh, I see. So I think we'll do something similar. You know, like push dupe and push drop. That we'll use instead of doing this sort of thing. And that works on some sort of bodybuilder, pesto bodybuilder. It's called builder here. I want to dupe some value. So what the way it works is that we have we get the value on a fun builder. On a fun. So we have a fun and we have a builder. What is what? Fun is the pudding fun. And builder is the pesto body builder. Okay, so I'll just take the pesto ID, I guess. And that's it. Also a type, I guess, the plum type. And this will be the plum type. And the argument will just be the pesto expression, maybe. Pesto ID. Pesto is not in scope, that is indeed true. And that entire thing should then return an ID. Okay, yeah, so we do pesto of dot call, pesto call of this function, compile dupe fun. Oh, it's a pesto ID. That makes sense. Yeah. And I think the first step would be compile dupe fun, rather than doing builder.push of something, we'll just do push dupe. Of an ID and the type. Yeah, that's a lot shorter. That's nice. But this doesn't work because it also needs the pesto. True. Now it works. Amazing. Same thing here. Builder.push dupe of builder.param. Variant of value is the thing we want to have. And here's the pesto. Boom. Yeah, that makes sense. If it's a pointer, then we immediately push the dupe thing. Same for closure pointers, yeah. I think same for, let's do the same for the drop function. So dropping a struct would drop the individual fields. So value, and the type is field value, and this is the pesto. Yeah. For the enum, we would either drop that if that's a pointer, or otherwise we would call the drop function, the corresponding one, which will be builder param and value being the type and pesto being the pesto. Amazing. And yeah, for lambdas we'll drop the closure pointer, that makes sense. Okay, and then we have this free function where we have the closure type, and then we, for every captured type, we drop that. Cool. Okay, yeah. Then we have these, and down here we have the dupe and drop. And dupe would just be, oh, I guess we return immediately in that case. Just builder dot push dupe of the mapping value of the type. That would be find get value dot type and the pesto. And same thing for the drop. Mapping value type pesto. Okay, so this shouldn't change anything. Oh, it returned 5. That's cool. Yeah, that doesn't change anything. But what we can do now is we can say if the pesto gives us a pesto type is recursive on a plum type, okay. Contains pointer on a pesto type. Oh, hang on, that's a plum type, yeah. Let's go into the pesto. I think there's a switch on pesto types. Yeah. So an int doesn't have a pointer. A pointer has a pointer. Struct has fields. And for every field, do if field value contains pointer, then return true, otherwise we'll just return false. And then for enum variants, well, if variant dot value contains pointer, then we return true, otherwise false. That's pretty amazing. Hang on, what? No. If the type to pesto if that doesn't contain a pointer, then we just return the original ID. So now we shouldn't even dupe the ints and drop them. And indeed, the waffle gets a lot shorter. And that's cool. That's pretty cool. Nice. Yeah. So let's look at the more complicated code now. This one. I think there will be a lot less clutter now. Still a lot of code, still, but not as much, you know. We have less casts, we have less dupe and drops. Okay, so we have these. We have a cast, we have this dupe and drop for lists. We have a plus function, which just adds the integers. That actually makes sense. Yeah, another drop function, sure. And still a lot of code, but not the same amount as before. So let's see what this. It returns 0. How about returning the length of the list? Interesting. Do we at some point not expand some recursive type perhaps, or something like that? Maybe. Okay, so let's look at this, make this. Yeah, and this is an int, this gets compiled to nothing, same here. And then we check if this int equals 0. The result is a bool. This compiles to nothing, and we switch on that bool. Yeah, if it's true, then we create an empty list with an empty struct inside. Makes sense. And we cast that. We dupe the result and then we drop these ones. If the length should not be 0, then we create these numbers. We subtract 1 from the length of the list. We call ourselves recursively with that length minus 1. We create a struct, put that inside as well as the 42. Then we create a more variant. Then we call, please cast this struct to this. Sure. Which then dupes and drops stuff. So the length, we dupe the list. That makes sense. I think this is actually where the error is inside, because all of the other functions, they existed for the sum as well. So somewhere here something goes wrong. We dupe the list. Okay. We switch on the list. Returning an int. That makes sense. Yeah, and then in the end we dupe that int, we drop the original list, and we drop that int another time. So it's only exists one time. Yeah, reference count is 1. So for the empty list, we just create a 2 that we dupe and drop, aka do nothing. We'll just return that. For the more variant, we take the rest of the list. Oh, yeah, this has an argument. I see. Take the rest, which is a struct. Then we say call something. Call list len recursively on that rest of the list. Then call plus on the result and 1 and return that. Seems reasonable, actually. Seems very, very reasonable. Okay, but still it panics. I guess first step, let's write down where... hang on, I'm kind of wondering, it doesn't tell me... It compiles something to pesto. Does it say that somewhere? It says this is the pudding, and that's it. Interesting. Let's Oh, indeed, it doesn't have this sort of, you know, introductory thingy. Is this horrible? I don't know, but it is pretty cool that you can do this. That you can just put them all next to each other. Okay. Yeah. Unreachable is what it says. And that happens when converting to pudding, to pesto. Yeah, now it says pesto and then unreachable. Okay. So pudding to pesto, what goes wrong here? Yeah, well, let's maybe do that even. Amazing. So pudding to pesto contains pointer on some pesto type. Let's see, we have this primitive type that is different than int. Oh, let's actually print something here instead. Hey, maybe that's actually it. Because we didn't change anything about how recursive types are, you know, lowered. Yeah, primitive type T is now a thing. Apparently when, oh, I think we don't yet do substitutions correctly. No, we probably don't. Yeah, compiling this function with item being t. That is not what we want. We want to compile the length function for item being int. And then it also makes sense why the sum function worked, because that was only defined for list of int, like a concrete type. Generic functions don't work yet. Oh yeah, but not today. Not today. Yeah, see you sometime. Alright, passing substitutions throughout the compiler pipeline. Basically, the problem is that now that we resolve functions in the egg, and this is also where we look for functions. Like here we go through all functions that are visible. Here we have the visible functions. We go through all of them, look where the name matches, then we look where the types match. And while we do that, we get these constraints and can use them to get substitutions. For example, for this maybe function, called the len function for lists, that works on this enum where we have an empty variant and a more variant where the item is a t. We call that on a list of ints. So when we find this len function, we actually know in these substitutions that t has to be int in order for that function to match. But we don't use that information. We use some of that here for error reporting, but apart from that, we just get these substitutions. We use those substitutions to calculate correct parameter types for the functions, so that we can then later on cast our arguments to the function to the correct types that the function expects. But that's it. Apart from that, we don't use the substitutions. Well, what we should do is we should just store them, I guess, in this call somewhere in here. Yeah, we should just store this function with this signature, but also with these substitutions. That is, this function specialized for these types. And I think we have the substitutions, yeah, we have them available here, so let's just put them in there. And then in the next compiler stage, the yogurt, we can then apply these substitutions when we compile this call, so that we can actually specialize the function for those concrete types and generate multiple functions for every time that you use the function with. So I think the egg callee somehow needs to be adjusted. Let's maybe do that first. Here's the egg callee. The function just stores a string, but I think there should be some sort of matching fun. I know matching fun is already taken, I think, maybe. In lookup we have matching fun. I think we don't really use that though. Like, if I comment this out, will that, I think the code still compiles. Oh, maybe it doesn't. Yeah, collect all. Okay, that's a different error. Interesting. Hang on, look up in line 46 here. Oh yeah, I think with this, I wanted to remove that, or at least move that into the egg directly. Yeah, this still compiles. I promise some t. Yeah. So, what we want to do is, I commented this out, which means the name matching fun is now free for us to use. So in the egg, I'll actually store matching fun here. And what's the matching fun, you might ask? Well, matching fun is just the signature and substitutions. Yeah, and that's it. That does mean that when compiling a function in here, we'll need to not just put the signature in here, but also the substitutions. So let's do that first. And then we'll look at where this case is handled further in the compiler. So this will be a matching fun with the signature. What was that before, I think? It's just called signature. Yeah, signature and substitutions. Okay, perfect. Yeah, those somehow need to be printed. So I guess let's do in the egg, when printing the egg, down here, when we see this is this matching fun, we can actually write the signature and then we say this matches with these substitutions. I think substitutions don't implement printing. Yeah. Well, but I think that's actually useful to do. So substitutions, here it is. Yeah, let's support printing substitutions. On some writer that just does well, for every substitution in substitutions, horrible typing, we write down the key equals, well, that plum type that is in there. Something like that. And those are, well, joined with commas, but we don't have joins and higher order functions here, so we'll just store whether we're the first element. And if we are, then we'll just set that to false, otherwise we write a comma. So now we can print substitution, but not substitutions. Oh no. Okay, somewhere there's a typo. That's unfortunate. Substitutions. That is spelled correctly, I believe. Here it is. Yeah, writing is difficult. Oh yeah, so then when we convert the egg to yogurt, and we're like, yo, please call this function, this is a matching fun, we need to apply those substitutions. So here we can get, you know, the function signature, fair enough. And in our context, we already have substitutions, because we may as well have a generic function. If we are some function, I don't know, we want to calculate the average something of a list, for example. So we may be a function that works on any list of A. And the length function may work on a list of T. Yeah, we can use different type variables. That means when we ourselves are compiled for a list of ints, for example, and we call the length function, then we are actually called with substitutions, with A being replaced by int. When we analyzed our own source code, we found out that we matched the length function when the T from the length function is our A. So now we need to update those substitutions, applying the matching ones. Something like this. Yeah. That is pretty cool. I think this doesn't work yet, though. So, what's going on here? Yeah, I think I'm just going to write a specialized function for substitution, which doesn't exist, so let's do that. Let's maybe move this down somewhere here, because this is really not the core logic of that. Okay, we're specializing types with some substitutions. But we should also be able to specialize substitutions themselves with other substitutions, resulting in even more substitutions. So by kind of merging these two mappings. Yeah, the way that goes is that we take our substitutions, yeah, and the result is going to be a map function string to clone type wrapped in substitutions, and then for every entry in a dot substitutions, we basically do result dot put entry key entry dot value dot specialize with b. True. In actor yogurt dot yeah, here we need the signature. That's just matching fun.signature. Oh, hang on, no, not quite. That is just fun. This one. Okay, that doesn't work. Interesting. Why not though? We have the yeah, let's maybe look at the individual compiler stages. For example, here we have the maybe function. Maybe function unwrap works on some maybe of t, and it calls the maybe unwrap function, takes a maybe and a string, and it calls that with t equals t. So this t right here is set to our t right here. Do we have something where we don't have t maybe as maybe not. I'm way more interested in the list length function, so let's look at that. Yeah, there's the pudding. Before that is the yogurt. That's this right here, and before that is the egg. And somewhere in here there should be a length function. List get, that's already pretty cool. We have a list empty with t equals t. List.sum. Here's the len function. Okay, so here we call the len function with t equals t. Yeah, we call ourselves recursively. That makes That makes total sense. And the other function I'm interested in is the main function. Where's that one? We have call list, int playground, make list. Here it is. Yeah, it calls make list, and then I call the list.len with t equals int. That seems correct. Because this is a list of ints. That's how this matches this generic function. Fair enough. Okay, so we have that. Then next compiler stage, the yogurt, would compile these functions. So it would compile the main functions, several cast functions, and also the length functions, resulting in these: the main function, make list function, several casting functions, and also the len function that works on any t. I mean, it needs to be in the signature somewhere, so when we compile the singular function down here, we need to, we do. This signature should actually be based on the specialized parameter types. That is interesting, because then the signature of this function should not be list.len of this thingy of t, but there should be an int here instead of t. Yeah, let's just print the substitutions, why not? Okay, so this is the yogurt. We compile main and make list and equals and several cast functions and minus make list, several cast functions, several cast functions. Oh, and now we compile these list functions with no substitutions. Where are they? Interesting. So here's our handling of a call. We say these are the merged substitutions. Is it the wrong way around, maybe? Yeah. I think we should take the function substitutions and take those as the baseline, but specialize them even further using our substitutions. So if we find out, hey, this function matches with a equals b, and we are now in a context where b is int, we want to have substitutions where a is int. Okay. That makes sense, actually. Oh, yes. That looks better. So we have a list.len function that takes this, a list containing integers, Amazing. Yeah, but still the T is somewhere in there. I'm not entirely sure where, but well, I guess at some point we use types and don't substitute stuff. It's kind of difficult to find though. I'll admit, like, we compile this function with these substitutions. So let's just roughly go over this, see if there's any obvious thing that we forget. The signature incorporates those substitutions. This all works on the signature, even including like this, the context being defined. Then there's this part where we don't deal with types directly, we just say, hey body, please compile yourself with these substitutions. And then the body receives those substitutions, and it has parameters. Yeah, and these should be, I believe, for every parameter we push a parameter, and that type should be specialized for these substitutions. The parameter types are specialized. Now let's see if that is enough to fix the problem, but it makes sense to go through this carefully either way. Then we put something in the mapping. Okay, and then for every child we get the corresponding expression and we compile that. In the end we get the body. That seems right, and when compiling we pass on those substitutions. So here's that. The type that we expect is definitely specialized based on those substitutions. That makes sense. Yeah, and these don't use the type directly. They immediately use this substituted type. So these should all use substitutions as well. Yeah, this as well. Lambdas will be kind of difficult, I guess. Oh yeah, this for example. Here we may, yeah, those lambda parameters, I think they need to be specialized actually. And we track which things they capture. Oh, but this is not the egg body, this is already the specialized version. The specialized, the yogurt bodybuilder containing only specialized types. So it's fine if those, it is fine to get the type of those. Yeah, these are the captured variables, which is, by the way, weirdly indented. It should be like this. Then we go on to the parameters. Oh yeah, these, again, same mistake, should be specialized for these substitutions. We create parameters of that type. Okay, the children are compiled normally for our substitutions. And we have this that contains the source, but should also contain the substitutions. Because the lambda is unique for that. Lambda, the source contains the module, it contains the line numbers, and now it also contains the substitutions. So this signature should really be unique. And then that is returned. We don't do anything with types except the outer type that is already specialized. Here we just get the parameters. We see is that a call, is that a lambda, then we emit a lambda call of that specialized type. If that is a function, we specialize that function, merge these substitutions, resulting in the call. If this is a built-in, then we need to do something. If that is a cast, then this is the expected type that is already specialized. Okay, that is fine. It actually runs through. That is pretty cool. It does produce the wrong result, I believe. Yeah, making a list of length 2 and then getting the length should not result in 0. But apart from that, you know, pretty nice. Yeah, there are probably other things I can do to make this more easily debuggable and simpler. One of them being to remove a lot of the dupe and drop stuff that's happening. Yeah, another to do basic constant folding, but not, that's kind of dangerous, not too much so that we don't do anything at runtime. But yeah, we have a nice specialized functions now. That's pretty cool. Okay. Yeah. Yeah, I guess that's it for today. Here we are again. Yeah. It is weird that this thing still doesn't work. Like currently I have this code in the main function. You know, it creates a list of length 2. I think that's the length, which should be 2. But it returns 0, and I have no idea why. I've done several things to try to make this more easily debuggable. I've made it so that most of the dupe and drop operations are actually omitted. Like if the thing doesn't, if the value doesn't contain a pointer, then it doesn't need to be duped or dropped because it's just copied anyways when you use that at some other place. Yeah, only pointers and heap allocated things need to be reference counted. At the same time, I also removed some casting stuff. But now I'm kind of lost. Like things still don't work apparently. Yeah. So I think let's just review this. I mean, there's not a lot of code. You know, make list of 2. Let's review the code and see if that's correct. I mean, but I already did that. Okay, you know what? I think let's make sure. Let's maybe print which instructions are executed, because as far as I can tell, everything I've read so far seems reasonable. So maybe the problem is after the bytecode, after the waffle. Like the waffle 2 bytecode generation, maybe that's going wrong. Yeah, we can't really easily print the bytecode though, or at least it's probably a bit confusing. Yeah, we have this. Let's do this. Let's print all the instructions that are executed. Maybe that leads us somewhere. Oh yeah, that's gonna be fun to debug. Quite a lot of code. Okay, maybe let's go through this and kind of try to assume what's going on. Hang on, what do we think is gonna happen? Oh man, we have the main function, which lives somewhere here. Waffle is dupe cast plus drop. Here's the main function. Okay. So we do stuff. We have an argument that we really just ignore, but we unpack stuff from that. Okay, so we're gonna see something like that. Then we'll call the makeList function. Makes sense. We'll dupe that. We call the length function, and then we drop that. The makeList function, I saw that somewhere here, yeah. That just checks if the list is 0, if the length should be 0. Gets the arguments, unwraps them. Yeah, compares the int that you pass in, which is available at as this at 0. It gets that int, this one, and it creates a 0, this one. And then that int and 0, it compares them using these, by calling this int equals function. If the list should be 0, then it just creates something. 42, apparently. Interesting. It takes that 42 and oh, this is false. Oh, that makes sense. Yeah, if the list should not be 0 long, so this is the false variant, 0. And this is the true variant, I see. So if the length of the list should be 0, then it just creates this padding, this node that contains, well, I would have said a lot of padding, but not really. It's just 1 byte. This is size 0. This is size 0. This is 1 byte. It's just a tag saying this is an empty list. This one. It's this. And then that gets cast to this other giant type. Fair enough, and it returns that. In the case where the length should not be 0, it subtracts 1 from the original length. Yeah, it calls itself recursively with that result. Okay, creating a list with lengths. Oh, I haven't shared my screen. Not even the correct one. Do you want to start over? No, probably not. This is fine. Okay, I'm just going through the waffle, seeing whether that makes sense. But so far everything looks good, which is a bit confusing. Like, makeList looks fine as far as I can tell. You know what, let's look at the instructions that get executed. I have a rough idea of what's happening, so. Okay, we do some stack stuff. Then we call, oh, this is probably the equals function that checks if 2 ints are equal. So it does some stack stuff, then it calls the probably built-in, like, the equal function calls the compare ints function, I think. That does stuff. Ah yeah, and it actually subtracts 2 numbers, compares them to 0, pushes that, okay, compares them to 0, that results in either they are equal or they are less, or they are like either the number, hang on, we compare 2 numbers by subtracting one from the other, comparing the result to 0, and that is either equal to 0, it's greater than 0, or it's less than 0, something like that. So we have this jump table of one of the 3 possible things that it can be. Then we have another call for some reason, we have another jump table. Okay. And here we return from that inner call, here we return from the int checking function, and then we have yet another call, return, call, return, something. Is this the jump table in the main function? Maybe. This is just a lot of stack stuff that's going on, which is unfortunate. I'll have to optimize that. What's wondering me though is there's no malloc as far as I can see. We should allocate list nodes, I believe. Make list. Make list is defined here. And this allocates list. Is the length is 2. You know, let's check if equals works. It should work, but I don't know at this point. Yeah, the length is 2, so let's put a 2 in here and see what that does. Either 42 or 43 is what it returns. Sure. And hexadecimal, that would be 2A and 2B, I believe. Okay, is 2 equal to 0? Yeah, right. That is nonsense what I wrote. If 2 is equal to 0, then we exit with 42. Otherwise with 43. Like that. Yeah, okay. Wait, what? 2 is equal to 0. Okay, that is not a lot of bytecode. That's pretty cool. Can we trim that down further? Like, one thing I learned writing compilers is that the best, like, debugging programs is pain, and the best way is to simplify things as much as possible. Equals comes from the int module, which is defined here, and that uses compare ints to do something. So, or even import that. That's convenient. Yeah, so let's do compare ints 2 and 0, and that can be less or equal or greater. The bytecode fits on a single page. That's nice. So we push a 2 and a 0, the two numbers that we want to compare. Fair enough. Then we push something from the stack at offset 8. So we skip the 0 and we push that 2 again. Then we push the 0. Okay. So then we subtract, like 2 minus 0. That would be 2. We compare that to 0. Push 7 bytes of padding, I mean, sure. Then we push that byte that this put onto the stack again, and we jump on that. And that causes us to push 43, which is equal. I think compare ints is broken. How is, hang on, something 2, oh, what is it, 2 bytecode. But hang on, no, the bytecode seems correct. Like, at least it seems reasonable. What's below the bytecode? We have the VM. Yeah. Compare 0. What do? We pop an integer. That makes sense. We compare that to 0. Oh no. Okay, I'm kind of happy and kind of sad. So this is weird. Like, when did I write this? The point is that our structs and enums, the memory layout should be independent from the ordering of the variables. Because if we have one enum somewhere defined as true or false and another enum as false or true, those are treated as the same type. So values of these two types, these two enums, they should actually be the same, and they should have the same representation. So we sort inner variants alphabetically when assigning tags. That does mean that equals should have the byte 0 actually. Why? But I think like this seems so random that I overlooked that. That's strange. Is that alphabetic? A, B, C, D, E, F, G, H, L, J, K, L. Okay, yeah, that seems reasonable. Yeah, this also does not seem correct. Or does it? Hang on, let's think through this. Yeah, we have integers on the stack. Like 2 and 0. What the sub instruction should do, it should just calculate. Like if the stack contains 2 and 0, then the stack, then the sub instruction should calculate 2 minus 0, not 0 minus 2. But when popping integers, it actually pops the 0 first and then the 2. As we have A and B on the stack in that order. Yeah, vm.popInt first pops B before popping A, so we calculate B minus A. That is also wrong. I mean, for the plus it does make a difference, I guess. How did I never notice that? Like, I had Plum code working that allocated memory, created lists, stuff like that. How? Even mapping functions. I don't get it. I really don't get it. I mean, this seems kind of, complicated, maybe. Maybe I should switch that around, Nah, I think this is fine. So we have plus, minus, multi times, we have divide. Okay, this is divide, this is multiply, this is subtract. Then we have mod, which is actually that mathematical modulo, not the remainder operator like in C++. I mean, it doesn't really make a difference, I guess. Hang on, let's create something like pop 2 ints and then use that. Nah, I don't know. I guess this is fine. Hang on, and to integers, that's just an ampersand. Oh, this is the OR function. Interesting. And XOR is that thingy. Oh no. Yeah, so let's maybe put parentheses around that because OR is also an operator. Yeah. Not at all confusing. Okay, I mean, it's a common theme to first pop things and then do stuff. Yeah, so I guess that's fine. Oh man, that is devious. Like, so low level. I didn't even consider there could be something wrong with that. But also because like this existed for a long time, this code. Okay, so 2C, let's see. That would be this. Compares 2 and 0, 2 is greater than 0. 2C, yeah, that makes sense. Okay, let's try the make list. Make list of length 2 and then call .len. Please work. Please work. It works. Okay. Okay. So I've basically fixed the compiler. That's nice. And that is like this was like 18 minutes into this, into today's coding. That was quick. Yeah. I mean, I know that I did a lot of stuff in this video, so I'm just going to clean things up a bit. I won't do too much else. Yeah. Okay. Okay. Speaking of cleaning things up, I have a version that works at least, so I think it's time to commit that, and then we can still refactor stuff and do things more beautifully and so on. Then we really touched like everything, even. Yeah. Okay. You know. Let's go through this and kind of review the changes and adjust minor things. Maybe. Can I zoom in here? I would like to zoom in, please. Does it work? Control plus doesn't work. That is. Oh wait, what? Zoom in is Control plus equals. Why would you do that? Why would you ever do that? Oh. Oh no. Oh, where's my equals sign? Usually it's there. I don't know. Okay. Okay, it doesn't go any bigger than this. Okay, that makes sense. Okay, yeah. Printing errors, sure, that is fine. We have introduced a generic DAG. Okay, actually we might want to use that in the other compiler stages as well, not just in egg and yogurt. But that will be a separate commit. Yeah. The built-in signature, by the way, weird name for that. Weird name. Has this. Okay. I guess. Yeah, the instruction, I want to remove that long term and instead have, build several called built-ins on different levels. In the yogurt we might remove some of the built-ins and instead of other built-ins and so on. Okay, bacon, nothing changed. Toast, oh yeah, stuff changed. Oh right, imports now have signatures. That also happened. Like, that is a lot of code in one commit. Yeah, we can now compare toast types, which I guess, sure. Yeah, import and exports, they got kind of a lot of stuff. Yeah, the printing got adjusted, that's nice. Okay, so when casting and when passing bacon to toast, we refactored that from just having different methods for passing item, passing undotted stuff, just have one pass expression that has allow white space and allow dots in there. What's going on here? Oh yeah. I mean, it probably makes sense long term to split the parsing up into multiple files as well. This is also over 1,000 lines long, I believe. Oh, not really. Okay. Yeah, but still, Okay, and the egg. Oh yeah, the egg changed completely. Here we have egg funds in a map instead of just a list. Egg funds got simpler. That's nice. There is no built-in separate thingy to handle here. That's just a normal operation, how they're now called. The expressions have types. Damn, a lot of stuff changed here. That is nice. Yeah, that seems correct. Then the yogurt is down Oh, hang on. First we've reviewed the egg. Let's now look at toast to egg. Oh yeah, and that got split up onto multiple files. And we have a separate thing for tracking visible variables. Makes sense. We have a separate section just for compiling types. That is nice. We now have this stack, which I believe we use, yeah? Oh, no, we don't use that. We don't use these two modules here. But I still think it's fine to keep them around, you know? Yeah, we have this to do here to remind us of that, so. Okay, here we have the lookup uncompiled fun. Oh, this seems a bit fishy having that commented out code in there. Well, oh, that is an important to do. Yeah. To be clear, like in production code, you know, I wouldn't leave in comments and to-dos in here. But this is a hobby project. It's something I do in my free time, and at some point this will be finished. It's not like, you know, there are no changing requirements. There is no, you know, this feature-driven, sprint-driven development. This project is not in a rush. Which means that I'm taking my time. It is fine to leave unfinished stuff in there. It's fine to leave to-dos in here. It's even better probably than having GitHub issues and stuff like that. At least for my personal to-dos, you know, because I can just, like, this is my personal code base here. So I think it's fine to not be strict about that and instead embrace this, you know, having one state of the code base instead of branches and stuff. Yeah, just this will evolve and settle and be cleaned up over time. But it takes time. It takes time to figure out these things and figure out the correct abstractions. And having clean code is currently not my priority. My priority is having a compiler that works and that the intermediate stages, they have clean abstractions. Then later on documenting that and cleaning up the code itself and stuff like that, that makes sense. But we'll get to that. And if not, because I abandoned the project, then that's, you know, that's also valid, and I haven't spent time satisfying, you know, sacrificing, brainstorming, and trying out ideas for code quality. And currently, I feel pretty confident with the code quality. And you know, there were to-dos, there were commented out stuff. There are probably bugs, but I feel comfortable in the design and the architecture. So that's the main thing I'm concerned with. Okay, here we have the egg to yogurt, also split in two parts. That makes sense. The casting part and the mod. Okay, yeah, we have the egg to yogurt. The yogurt gets followed by the pudding, which didn't change. That is nice. Yeah. Very, very nice. Okay. Oh yeah, this can be removed. Here we match things with mutable stuff. That makes sense. That's actually a bug fix. Sure, new line is always fine. Yeah, specializing substitutions. Amazing. Next, the pesto. Oh yeah. Better printing, sure. Optimizations around dupe and drop. And also cleaner code in general, like shorter code here, just one line instead of pushing calls and having the same logic everywhere. That's always nice. Okay, yeah, this one was just for exploration of and explanation of this function behavior, so I'm gonna discard that. Yeah, and then we only have standard library stuff and this one. Oh yeah, import the correct file, that makes sense. And this one, I mean, this makes sense. I'm probably gonna leave this commented out, this standard out print. Yeah, these are all refactored. Boom. Okay, and then we only have the standard library. Oh yeah, a lot of all the imports and exports changed, which makes sense. This now works. Yeah, that's pretty amazing. Okay, so really I did a lot of stuff. A lot of stuff. Amazing. That's pretty cool. Okay, what else? Not just what do I want to do next, but also, is there something I should still do in this video? Do I want to clean up code? Do I want to, you know? There were to-dos in there, which still need resolving. Oh, damn. Yeah, that is just, nope, nothing will do today, at least. Maybe. Yeah, I can actually do that, because I can just do get a module equals speedup module. This was prohibitively expensive when I just had the file content, but now I have the module, so sources doing ... sources, not sources from different modules. Yeah, want to do this. Yeah, this is an open question. That's true, but yeah, not really actionable, you know. Oh yeah, that is a to-do. Ooh, it's just hacky. Alignment. I'm not even sure what that means. Well, allow body. Again, not sure. Oh yeah, that is an important to do. But I'll get to that when I kind of have multiple avenues on what I can do next, but yeah, that's just that. Here's monomorphization. If we compile the lambda for different types, we do that. Yeah, we do that. We have lambda with these substitutions. So the types, they influence the signature, so that the lambda is still unique. Oh yeah, that's actually an easy to do. You know, let's do that. Basically, we have a struct. If multiple fields have the same name, that should be an error. So if field dot if fields dot contains the name, then we'll actually just return error, and at the error of name is in the struct multiple times. Yeah, and this is the toast, I believe. Yeah, so we have the ampersand here. That's pretty cool. So we can just show that error at the ampersand from the start. Amazing. Yeah, so now we do that. Pretty cool. Pretty cool. Oh, I didn't fold this in. Let me do that for the ones that I don't want to handle now. Oh yeah, this is actually important. I mean, it's kind of I mean, let's I think we should have a, and how does that work even? We have the case compilers and we switch on the cases. And we'll just do variant types.get of that symbol. I see variant types being a map, probably. Yeah. So what we want is, first of all, we should check that no. I think let's just create a set. You know, handled variants and a set of strings. So we want to make sure that no variant is handled twice, that all variants are handled, and that no extra variants are handled. Amazing. So first of all, for every case in the switch cases, basically we want to do, you know, if handled variants, if that contains case, what is a symbol, name, something like that, case.symbol string. If that's already in there, then we just return an error attached to the switch percent punctuation. And what we print is, you know, the string, so case.symbol string, sampled multiple times. Boom. Then we want to check that all variants are handled. So basically for variant and variant types, basically want to check that the key is in, you know, in handled variants. So if handled variants doesn't contain the key, then we want to print an error. I want to show, hey, this variant is not handled. Okay, and then we want to make sure that we don't handle any additional variants. So basically for every handled, for every variant and handled variant, we also want to make sure that you know, variant types contains that variant. Contains, probably. If that's not the case, we'll just say handle non-existent variant. Boom. Yeah. non-existent variant. Okay, important to-dos. Yeah, make sure that, oh yeah, that is actually important. Oh, yeah, many things here are important. But I don't want to do that now. I don't want to deal with that. Yeah. So that we call some lambda. Oh, that is important. That is really important. We know we have some lambda. We have the lambda type. So now we want to make sure that the arguments are important. Then also probably this right here. Casting the arguments. I'm not sure where we do that. And we have expected archetypes. We have that here as well. It's just called lambda type dot args. Okay, anyways, what we do is we cast these arguments. Then we call the function. Yeah, so we go through the args, we go through the lambda type. That is a plum type, I think, so that would be this one. That has args, yeah. Yeah, basically we want to check that the arg body, the type of arg is assignable to expected type. Basically that. Or we say with one types. On the name. Something like that. Ooh, okay. Yeah. We've done that. Beautiful. Yeah. And a multiple function that that is, I should do that, yes. But it's also something that I believe I'm unlikely to do accidentally, and which I'm just not gonna do. I know. Yeah, more elegantly, that is true. That is also true. Don't special case built-ins here. Oh, run function is also not important at all. Yeah, that's just a convenience to do. There's check for updates. Yeah, check for duplicates on. In the struct, when compiling type. Oh yeah. Yeah, same thing. Same thing. So if same thing as on the value level, we have the same problem on the type level. If there's already a field with that name in there, then that's an error. Do we have an error? A return at least. Well, good enough for me. That would just be the struct. Contains multiple fields named that. Oh yeah, and this also needs a location where to report the error to. We have a toast type. Does that contain any sort of source? I'm afraid not. Let's see. We have a toast type that contains... Oh, I mean the fields, they have names. So we can just do, you know, field not name not source. That makes sense. Oh, in the long term we could even underline both fields or something like that. Yeah, no, yeah, same for enums basically. So variance contains the variant name string. Then we whine about the enum containing multiple variants with the same name. That is cool. Oh yeah. I have no idea how, like, yeah. I don't know. Oh yeah, that is something. Again, hang on, where are we? We have that in compile. We do already have compile of toast type with defs. Hang on. Where do we do that if not there? Here. Compile toast type with that environment, parent calls and stuff. What? Why is that a different thing? Is that even used? Or is it this one used? Oh, it is used here. Type. Prefix calls with module. Hang on, is this one used? Compile the module with defs. No, here we have the full deal, like env and the list of ongoing calls and so on. I think these down here are not even used, these functions. Well, let's try that out. Let's remove them. See if that still compiles. No, it does not. What the hell? In lookup. Oh, okay. I kind of hate that, to be honest. Like, oh, we have two separate compilations for that. Yeah, so byte doesn't really exist yet. power, we can take the power more efficient. I'm not sure about that, but we can, for certain, do it in a cleaner way, where we can just say, does the exponent equal 0? That's just going to be 1. Otherwise it's going to be base times, instead of doing that here, base times that. I don't know about efficiency. I can make that more efficient if I want to, but this is damn short, so yeah, I'm not sure about that. I think I'll actually maybe it makes sense to kind of go through the standard library, write some functions, write some stuff as a separate video probably, cleaning things up, stuff like that. And make sure this compiled. It doesn't, of course it doesn't. Call the function source. Okay, sure. Let's do it like that. I don't know about that. I don't know. What? Let's maybe print the ones that are handled. Oh, we don't put them in there. Well, yeah, that makes sense. Yeah, no need for that. Yeah, empty struct, empty set, makes sense. Okay. Yeah. I think I'm going to stop it there for this video. Whew. Maybe I'll commit that, do some general cleanup. Okay, yeah. This video is way too long, so I don't know how long it is, but it was several days of programming, so yeah. To be honest, I intended this to just be a small okay, you know what, let's first kind of reflect on what I did and then reflect on how I chose what to do and like the workflow in general. So first of all, I like that I made the parsing more robust, that now you have to include entire signatures like plus of string and string instead of just saying plus, and like all plus functions defined in the module are automatically imported. That makes it feel a lot more robust and a lot more controlled, this import-export stuff. I like that I fixed several bugs in the VM so that things now compile and that you can do make list of 2 and .len and you actually get 2 as a result. and the list gets allocated and freed and stuff like that. That is pretty amazing. I like that functions are now checked independently, that rather than having to use a function from the main, in the main function, you have to use the function or somewhere transitively in order for that to get type checked. That behavior kind of bit me in the ass a couple of times in Martinez. Even when writing the Plum compiler itself, I'm pretty certain actually that there are a couple bugs in the Martinez standard library and a couple bugs in the Plum compiler just because code is not used and code is not analyzed, and there are some edge cases that I miss. And having type checking by default, type checking every function, is so damn useful, so useful. So I'm really happy that that is working in Plum now. That makes it feel like that makes it feel so much more robust than previously. And it even found some errors in the standard library. Like at some point we used the less than function rather than the less than symbol that we introduced later on. And like these are the kind of bugs that are common in Martinez, that I try to use some function, I try to use something that I haven't used for a long time, and turns out it doesn't work because it depended on something else, which I refactored, and I didn't get notified that I broke some code. Type checking everything, having type checking by default, type checking generic functions in particular, makes things so much easier. And also I like that the compiler looks a lot more, not clean, but at least a bit more tidied up, a bit more like it has intent. I feel like I focused a lot of the effort in the previous sessions on the compiler backend. I spent a lot of time in this part from yogurt to rest, yogurt to pudding to pesto to waffle to bytecode to VM stuff. Like this is just a lot of code, and there was a lot of stuff that we have to do, like memory layouts and reference counting and choosing stack expressions and stuff like that. There was a lot of stuff. But I'm glad that I took the time to focus on this front part of the compiler that is unique to Plum, that kind of makes the language be unique. And it's nice that that is getting along and that kind of settles. The egg felt a bit out of place before. The egg was kind of like, function, like local variables and functions, those names are resolved. But for functions, we just store the name and say, well, the yogurt's going to resolve that. We're going to resolve that when we monomorphize, when we specialize functions. That felt not clean. That felt like a workaround. Now we do one strict pass around that, the egg. We don't have any comp time stuff anymore. I have plans on how that could be added in the future, but I think it should be separate from the runtime stuff. And in particular, when a function works at runtime, calling that function with comp time known values shouldn't alter the behavior of the function. That's the main guideline that led me to removing comp time for now. And I think that is a good design, or at least a good, default behavior, good property to have. Yeah, it's nice that I also unified some stages, like having a general directed acyclic graph data structure that you can just put new nodes into and then get IDs back, and then your query IDs, and those can be like the toast had its own toast ID, and toast, toad, and a toast code, and toast expression, toast body, stuff like that, and the egg as well. Now those are unified. That's just clean and nice, and it removes some of the boilerplate and these idiosyncrasies between languages, because I have helpers for these kind of stuff. That those helpers are all the same in all the compiler stages. That's just boilerplate. So now having this uniform data structure is really nice. And I feel like that could also be extended to other compiler stages over time. But we'll get there. We'll get there. Yeah. Okay. So there's more at it. Even all the optimization stuff, like removing casts from one type to the same type, or removing the dupe and drop operations if there's no pointer, no heap allocated memory, and something that where we actually do reference counting operations. A lot of stuff I did a lot of stuff in this video, and I'm kind of sorry about that because I feel like this video got really out of scope. I started doing something I believe was contained, like the compiler front end, but in fact I ended up changing a lot of the language semantics in ways that were really fundamental. Like, sure, resolving functions is something that is quite fundamental to how the language works and how functions and types are specialized. And granted, a lot of the majority of the work was in the egg and yogurt. I basically didn't touch the bytecode or the pudding or pesto. There were some smaller changes I did, but most of that was contained in the front part of the compiler. That is really nice. But I think for the next next videos, I'll try to pick smaller sets of changes. Maybe I'll also feel more open to doing, videos that do like really small things. Like, for example, creating this general DAG type. That's something that was on my mind for some time. I was like, that might be worth it to do sometime. I think if I had like a separate session where I was like, you know what, I'm gonna clean up, well, not clean up all the compiler stages, but I'm at least gonna unify them and have this uniform graph data structures that they all share. And then I create that and I kind of build that into every compiler stage. That would have been something that is really small, that is really, it has a limited scope, and that would have been really nice. Now I kind of waited until the code was so messy and I didn't know what was going on while the compiler wasn't working, that I felt kind of forced to refactor and to simplify the code and to implement some very basic, very crude optimizations just to get a handle on what's happening in the compiler. And that is kind of, I want to do that more proactively, refactoring stuff and making stuff a little cleaner. That being said, this I'm kind of struggling with if this is a big project, and the time is where do I focus my time and effort on. I could focus stuff on making like this part of the compiler super clean, but then that's not, the language keeps evolving, the compiler keeps evolving for now. It is still, I'm trying to find these compiler stages. I changed something fundamental in 3 compiler stages today. Well, not today, in this video. But the point is that the code base is still not, I haven't figured that out. The architecture is still evolving, it's still kind of growing as I figure out more and more stuff about the language itself and how that's going to look and how that's going to behave. And so I don't want to focus too much time on polishing all the minor details when I could, figure out these more fundamental things, and then once those are settled, kind of see what are the common patterns among these compiler stages. Let's do something about that. But I think for now, this was a really, really big refactor, and I think maybe the biggest refactor that I had to do in this compiler. I think it feels optimistic to say from now on it's going to be smooth sailing, but I feel like now is somewhat of a turning point. The language feels quite different. It feels nice, like having type checking by default. It feels like the language kind of exists, and it gives you errors when you write faulty code, and it's kind of somewhat reasonably functional. So yeah, I think the next step would be to kind of get that, iterate on that, let that sink in, kind of work out, refactor parts of the compiler where there's a lot of to-dos, a lot of bloat, a lot of stuff. I think there's still, for example, this file, the parsing file, is really long, and I think it makes sense to split that into multiple files, similar to how we did that for the egg to yogurt and toast to egg compiler stages, compiler stage transformations, whatever. Some of that kind of not building new features, trying out different things within the language, but rather take some time to work on the compiler, maybe do some language features, but some really minor ones. Like I was thinking about having a different syntax for lambdas, or supporting the equal sign in function names, so we can have an equals equals function for comparing numbers instead of having an equals function with the name equals, stuff like that. Like these could potentially be like really simple videos, like I don't know, half an hour or something, and kind of do these kind of little chores, improve the language a little bit not every day maybe, but every couple days. And I think that kind of accumulates over time, having something that evolves gradually and that you work on just a little bit to make something that feels quite polished. All right, yeah, so that's kind of the next steps. And I mean, this video has been long enough, so I won't bother you with even more talking. And yeah, I guess see you in the next video. Bye.